the last lecture we talked about sigmoid and softmax. So as a recap, sigmoid is what we saw in the left. Softmax is something that we haven't discussed about, but it looks something on the right. Sigmoid is basically for binary classification problem and softmax is for multi-class classification problem. Now in this part we will actually solve a small problem to understand this concept of neural network to the core. Okay, so in earlier example we saw this diagram and we said that based on different parameters value theta naught, theta 1, theta 2, theta 3, these neural network behaves differently, and that's how neural network actually learns. But how does it work? I mean, to get a clear picture, let's solve a particular problem. Let's design a neural network that solves the problem of XNOR, which is nothing but xy plus x complement y complement. If you understand XOR and XNOR, XOR gives you the output 1 where we have odd number of ones, right? And XNOR is just the not of XOR. So I mean, we have binary values, that means x and y can take just two values, either 0 or 1. Yeah, so okay, let's see how does it work. Well, we have x y plus x complement y complement. It's nothing but x and y, right, plus the x naught and y naught. It's a basic simple mathematics. I hope you have already seen this. So let's see. So that means if I need to design XNOR, I need to actually design this function. So let's first of all design x and y. So I know that x, y and xy, right? So it's a binary value, that means it can take 4 values, something like this. So x and y means something like this, right? So we want to design a neural network that actually gives the output of AND. So input layer, what would be the input layer? Input layer would be 1, x and y. I already told you that we actually add a 1 to include the parameter of bias, and then this would be our hidden layer, which would have several neurons. Let's just visualize one neuron. So these would be the connections, and here would be some weights, and this function would be calculated, and the f would be theta naught into 1, that is theta naught, plus theta 1 x1 plus theta 2 x2, and we apply a sigma on it, right? That is the activation function. So let's again visualize what was sigma x, like this, right? So something like this. It simply was that if x is greater than or equal to 0, your sigma x would be positive. Let's say it's 1 right now. And if x is negative, then sigma of x would basically be less than 0, and this goes close to 0. That means sigma x will tend towards 0, or in our example we will assume that it will actually give us 0 because it would be a very small number. So that basically means that if this quantity is greater than or equal to 0, we would get 1, and if this quantity is less than or equal to 0, we will get 0, depending on what your combinations would become, right? Okay, so x1 and x2 can take fixed values, that would be 0 or 1. So these theta naught, theta 1 and theta 2 need to be tweaked in a way so that this combination actually behaves as AND operation. That means if I choose the right values of theta naught, theta 1 and theta 2, I can have if I give 0 0, the output would basically be 0. If I give 0 1, the output would be 0. If I get 1 0, output would be 0. If I give 1 1, the output would be 1. That means this behavior actually depends on choice of thetas. So let's try something. And before trying, let's make a small change in our input. So in our input, I'm replacing 0 with -1. That means now in the input I would have only values -1 and 1. Why am I doing it? It's because later you will see, as we solve various different problems, we apply certain mappings so that it favors us in the neural network. It depends on what kind of activation function you are using, what kind of settings you are using, what kind of model you are using. Every model sort of has their certain priorities, certain preferences. So right now what am I doing? I'm just replacing this 0 as -1 and 1 as simply 1, right? It's simply that change, and it won't affect us much because I know that all I need to do is 0 as -1, and whenever I see -1, it simply means a 0. Cool. Now let's see. So if I see the first combination, it says 0 0 0, and if I see last combination, it says 1 1, the output should be 1. So let's just randomly say, take some values. Let's say if I take theta naught as 5, theta 1 as 6, and theta 2 as 7, positive values. So if I give this 1 1 1, so if I put it here, it would be sigma of 5 plus 6 times 1 plus 7 times 1, which would be of sigma a positive number, right? And this would basically give 1. So for this input, the combination, these weights actually works. But does it work for this combination as well? So it would be sigma 5, now 6 into -1, because 0 is -1. Similarly 7 into -1. So this would be sigma of some negative value, which is good because I know that when sigma is -0, the output that I will get, so where x is less than 0, the output that I will get is 0. So good. That means this combination that I just first took also works for this. Let's try for this second value. So it would be 5 plus 6 into -1 plus 7 into 1. Now this would be what? Sigma of -6, 7, 1, that means 6. That would be 1. So this fails, right? That means I need to tweak these values properly. I need to somehow figure out a way to arrange or to change these values so that it favors our output. That means if you see here what we are doing, based on the output, we are tweaking the parameters so that the output that we get actually is in our favor. Okay, let's see some other combinations. If we see here that if both the values are -1, I should get 0. That basically means that the sum of this sum should basically become higher than this quantity, and in negative this quantity should become higher than theta naught. Then and only then the sigma of your input would become negative and we will get the negative output. Similarly for 1 and 1, I see that I get a positive output. That basically means this sum should also favor, so that means if both are 1s, this entire should basically, this sum should either be very high positive in comparison to theta naught, therefore the entire sum would basically become positive and we will get a positive output. So based on that, what do you think that we should take theta naught, theta 1 and theta 2? Okay, let's try something like this. So if I take theta naught as let's say -40, theta 1 as 20 and theta 2 as again 20. Why am I doing this? I guess now you can see this, because let's calculate this sigma value for first input. So it would be -40, so this is -1, that means plus 20 into -1 plus 20 into -1. So this would be sigma of negative 40, negative 40, negative 80. That means 0. So it's good, right? Let's try second one. So second would be sigma negative 40. Now this is negative, that means plus 20 into negative 1, and this is positive, so that means plus 20 into 1. So this is again sigma of negative 40, which is 0, and that's good, right? And similarly you will also get this one, because here only this value would become negative and this would become positive. Let's try for the last. So it would be sigma negative 40 plus 20 into 1 plus 20 into 1, and this is sigma of 0, which is again 1, because I told you here if x is greater than or equal to 0 we get 1 or close to 1. So that means this weight combination actually behaves as AND. Now how did I take it? It's just trial and error. Yeah, right now it's just trial and error. So you try different combination, and based on certain findings you can tweak these values, right? Because here I knew that if both are 0 the output should be 0. So that's why what I did, I take this as negative value and this would become negative, this would negative, all the sum would basically be positive, right? And similarly if it's 1 1, I knew that the sum of these, since this is negative, the sum of these two values should be higher than or at least equal to this value, so that it becomes a 0. So that's why based on certain findings and certain test cases like trial and error we can actually get these outputs. So that means, okay, so what does that basically means? I don't know where did it came from. Okay, so based on these findings, if the AND can be designed something like this, so 1 x y, so this would be negative 40, that means theta naught would be negative 40, and this would be theta 1 would be 20, theta 2 would be 20. Now this f would now behave as AND, because now when we do this combination this would become AND, right? Now let's do OR. So we have another, which, where was it? This is OR. So let's try OR now. That means x or y. Right? So let's see now, the function f would be again sigma of theta naught plus theta 1 x1 plus theta 2 x2. Let's see what we can try. Let's right now start with giving positive values to everyone. Let's say I take theta naught as 40, you know, and then let's say theta 1 as, I don't know, maybe 30, and let's say theta 2 is again 30. Why? Because I knew that only for this cases the value should be negative, and so if for this basically to become negative, since they both are minus 1, these two sums should actually become more negative than theta naught, then and only then the entire sum would become negative, right? So that's why I took this 30 at 30, because 30 plus 30 would become 60 and it would be greater than 40. So based on this, like for the first case it would be 40 plus 30 into negative 1 plus 30 into negative 1, so that would be sigma of negative 20, which would be 0. So this works. What about the second case? Well, for second case, if I take sigma 40 plus 30 into minus 1 plus 30 into 1, which is again sigma of 40, which is greater than or equal to 0. Similarly it works for this, right? What about 1 1? Well, if everyone is positive, so the output would also be positive. That means this combination also works. So for x or y, the neural network would look something like this. That would be 40 30 30. Now this f would basically behave as OR. Now we have everything for XNOR. So for XNOR we have x y plus x complement y complement. Okay, now let's see, we had xy. Now what is x complement y complement? Well, it is exactly same as xy. Why? Because if you see, xy is 0 0 0 1 1 0 1 1, right? Then x complement would be 1 1 0 0, y complement would be 1 0 1 0, and this is exactly the same. If you see 0 0 0 0 0 1 0 1 1 0 1 0 1 1 1 1, so the same weights would also behave, the same weights would also be work for this network. Now let's create the final XNOR network. Okay, so for XNOR, so we have input as 1 x y. So the first hidden layer, so first of all, okay, now if I make these weights, what was the weights of xy? Negative 40 20 20, so it would be negative 40 20 20. Now this output will give the AND, right? Again I take another neuron, weights here, and the same weights, negative 40 20 20. Now this would give xy and this would give x complement y complement, right? Now we need to just do OR. So if I take here 1 and just give the weights of OR, which was 40 30 30. Now yes, yeah, one important point here. Now if you see here, I need another like where is 1 here, right? Because yeah, so just like as an input we add 1, in all other hidden layers as well we add an extra neuron that is always there, but it's actually not shown in the diagrams. So that is always there, and we just give it as an input here. So this would basically be +1, or I can give us some constant c, and this would basically be 40 in here. Now this would basically give the output of XNOR. Now if you see how neural network is working, it's simply combining several small functions to give the complete output, and every neuron is actually doing a separate job of finding something very simple. Like for example, this was finding AND, this is also finding AND between x complement and y complement, and based on that result we are getting OR. So that's exactly what resembles with the first diagram that I showed you, that in image classification or image processing, this first layer actually learns very small basic things like edges or corners, etc., and based on those edges and corners it aggregates them to the next layer to become more circulars or some other important features, and then we have several other layers which sort of combines this information, and in the end you get a face. So the idea is also same, but of course in a real practical situation you won't just have 2 neurons, you would have many neurons. I mean, you would get a network of millions and billions of parameters. That means these weights, theta naught, theta 1, theta 2, there would be millions and billions of. So just imagine how complicated that function would be. But in the underline, everyone is doing the linear combination and then just applying activation function on it. So that is how neural network works. And now another important point that you might be wondering, that here we just use trial and error to tweak the weights, but how does the network tweak these weights, right? How does this network tweak these weights? This is a very important point, and for this we have the gradients and the back propagation. So this would be another lecture, and I would also explain this by a small example so that you feel comfortable. So I guess that's it for today, and I hope that now this concept of neural network is clear to you, as in how it works. And I'll see you in the next video. Radhe Radhe.